In Worksheet 5, we're going to focus on solving trigonometric identities. So we're going to be using each of the cofunction, the even and odd, the Pythagorean, and the reciprocal identities in order to simplify some complex expression and reduce that down to something much more simple. Now, while there are many ways to go about approaching these problems, I've developed sort of a strategy that I think is the easiest way to start off when you're beginning solving some of these trig identities. Sort of my first thought is to think of these like a puzzle and less like a math equation. So that's why I've labeled these the trig puzzle solving tips. So the first tip is to have only one angle. So several of these problems are going to involve negative angles and complementary angles, being the pi over 2 minus theta. So my first tip is to get rid of all of those using even and odd identities or cofunction identities. And that's going to make life quite a bit easier, and it's a great place to get started. Tip number 2, if you have a squared trig function, chances are you're going to want to use a Pythagorean identity with that squared function, since that's the one identity that deals with square functions. So most of the time, if you have anything squared, you're probably going to want to use a Pythagorean identity to simplify that. Tip number 3, in the event that we have some sort of complex denominator, some denominator that has more than one term, so maybe it's like 1 minus cosine or cosecant minus cotangent. Oftentimes when we have an ugly looking denominator like that, multiplying top and bottom by the conjugate of that denominator will help simplify things. And then my fourth and final tip is if you've tried all the other 3 things and you're still not at a place where you know what to do next, try changing everything to sines and cosines. And oftentimes that can simplify things as well, or at least keep you moving. So with that in mind, let's go over some of the problems. All right, in problem 1, we've got cosecant over secant, and we're asked to simplify that. Match it to something in the box on the right. So I don't have any cofunction identities or even an odd or Pythagorean identities to deal with, so I jumped straight to changing everything to sines and cosines this time. So I'm going to change cosecant to 1 over sine and secant to 1 over cosine. From there, if I'm dividing by fractions, it's the same as multiplying their reciprocals, so I can simplify that to cosine theta over sine theta, which using a reciprocal identity I know is cotangent theta. So over in the box on the right, I'd want to choose option B, since this thing would be equal to cotangent theta. Problem 2. So this one has both a cofunction identity and an odd identity in it. So I'm going to start by dealing with those 2 things first. Secant of pi over 2 minus theta, that's a cofunction identity, so I'm going to want to change that to cosecant theta up here on the top. And cosecant is an odd function. So if I have cosecant of negative theta, that means I should pull the negative out. Then I have a factor of cosecant on both the top and the bottom, so I'm able to reduce those 2 factors, leaving me with just 1 in the numerator and negative secant in the denominator, since that negative that came out of cosecant is being multiplied, not subtracted. So I should get 1 over negative secant theta. And then I can use a reciprocal identity to say that 1 over secant is equal to cosine. So my final answer is negative cosine theta, which is option F. Problem 3, secant squared theta minus tangent squared of negative theta divided by secant theta. So the first step that I want to deal with is that negative theta. And tangent, I know, is an odd function, so I'm going to look just at tangent of negative theta and hold the squared out for a moment, since the odd identity only applies to each of the base 6 trig functions. So tangent of negative theta should come out to negative tangent theta, because again, tangent is odd. Now that whole piece, that whole negative tangent theta is what is getting squared by that tangent squared. So when I square negative tangent of theta, I end up with positive tangent squared of theta. But I still had the negative from the problem that stays here. So ultimately it ends up being a triple negative, so that tangent squared, so that numerator is going to remain secant squared minus tangent squared. From there, I can use a Pythagorean identity to say that secant squared minus tangent squared is equal to 1. And then 1 over secant theta is cosine theta. So option H. Problem 4, I don't have any cofunction identities or any even or odd identities. I just have sine theta times cosine theta times cotangent theta plus sine theta, cosine theta, tangent theta. So the thing I did first was change everything to sines and cosines. So I'm just going to change that cotangent of theta to cosine over sine and change tangent to sine over cosine. And then in each of these two terms, I have some factors that simplify. Term on the left, I have a sine of theta in both the numerator and the denominator. In the term on the right, I have a cosine theta in the numerator and in the denominator. Reducing those pieces away, I have left cosine times cosine on the left and sine times sine on the right, which is cosine squared plus sine squared. And I know from the Pythagorean identity that that is equal to 1. So option I. Problem 5. Again, I have a cofunction and an odd identity, so I'm going to deal with those first. Cosecant of pi over 2 minus theta is equal to secant theta. And negative cosecant of negative theta should become positive cosecant theta, since that's a double negative there because cosecant is an odd function. Then I decided to split this fraction into two fractions. So I have secant over the denominator on the left plus cosecant over the denominator on the right. And again, I'll have some things that reduce. A secant in the numerator and a secant in the denominator on the left, and a cosecant in the numerator and a cosecant in the denominator on the right. Reducing those pieces away, I'm left with 1 over cosecant plus 1 over secant. And then applying the reciprocal identities to each of those, I have sine plus cosine, which simplifies to option E. Problem 6. My first step is dealing with the odd identity for sine. So I have negative sine of negative theta. So that negative should come out, and that double negative gives me secant plus sine theta in the numerator, divided by secant theta. Then I elected to change everything to sines and cosines. So I have 1 over cosine plus sine in the numerator and 1 over cosine in the denominator. So I'm going to multiply top and bottom by cosine theta. Doing so will clear my denominator entirely, since cosine over cosine is 1. So I just have to simplify the numerator. 1 over cosine times cosine is 1, and sine times cosine is just sine times cosine. So for my final answer, I have 1 plus sine theta cosine theta, which is option K. Problem 7 is pretty straightforward. It's quite close to just a Pythagorean identity straight away. So I decided to show a couple extra steps this time. From the Pythagorean identity involving cosecant squared, I know that cosecant squared is equal to 1 plus cotangent squared. So I've just made that substitution in step 1. Afterwards, I distributed my negative and found that cotangent squared and negative cotangent squared add up to 0, leaving me with just -1. Option J. All right, problem 8 is a little bit longer, but again, if we follow our steps, the first thing I want to do is deal with any angles that aren't simply theta. So looking through the problem, I only catch one, and that's in this sine of negative theta up in the numerator. So I'm going to have to pull that negative out. So I have minus negative sine theta, which becomes positive. So sine squared plus cosine squared plus sine theta over tangent theta. Then I have a Pythagorean identity in the numerator. Sine squared plus cosine squared is 1. In the next step, I decided to change everything to sines and cosines, which only really left tangent, which is sine over cosine. On to that fourth step, dividing by a fraction is the same as multiplying by its reciprocal. So dividing by sine over cosine is the same as multiplying by cosine over sine. Then I just need to distribute that fraction. So 1 times cosine over sine is cosine over sine, plus sine times cosine over sine. Some things can simplify here. In that term on the right, I have sine theta divided by sine theta, so I'm able to reduce those. And in the term on the left, I have cosine over sine, which is the reciprocal identity for cotangent, which is option B. So in problem 9, I have a complicated denominator. I have this 1 minus cosine right here. And tip number 3 from the beginning was that if I have a complex denominator, I should try multiplying by its conjugate. Now the conjugate to 1 minus cosine theta is 1 plus cosine theta. So I'm going to multiply 1 plus cosine theta to top and bottom, right here. Doing so gives me the result of 1 minus sine squared times 1 plus cosine theta in the numerator, divided by 1 minus cosine theta times 1 plus cosine theta in the denominator. Now, foiling out that denominator, I have a difference of squares problem. So that anytime I have a plus b times a minus b, that results in a squared minus b squared, which is an identity from back in algebra. But it will be helpful to remember that identity because it comes up rather frequently in trigonometry. Now in the denominator, I have 1 minus cosine squared, which I know from the first Pythagorean identity is equal to sine squared. So I'm going to make that change. And now I have a factor of sine squared in both the numerator and the denominator, so I can reduce those two, leaving me with 1 minus the quantity 1 plus cosine theta, and simplifying that, I get negative cosine theta. So option F. And lastly, problem 10. Again, I have a complicated denominator, so I'm going to multiply by the conjugate of that denominator. And the conjugate of cosecant theta minus cotangent theta is cosecant theta plus cotangent theta. So I will multiply that conjugate to both top and bottom. Again, I have a difference of squares in the denominator, so that should become cosecant squared minus cotangent squared. And from one of the Pythagorean identities, I know that cosecant squared minus cotangent squared is equal to 1. which means that my answer is cosecant theta plus cotangent theta. Which is option E.